In this video, we're going to be covering momentum and impulse. So let's start off with the first question. A 200 kilogram car at 20 meters per second, and there's secondly, a 20 kilogram child walking at 3 meters per second. Thirdly, we have a 4 kilogram building that's at rest. List the objects from highest inertia to lowest and explain your answer. Okay, so we know that inertia only depends on mass. So you can represent this as I is proportional to m. So essentially, you just compare masses. So our building is 4,000 kilograms. Is 4,000 kilograms. The child, let's say, it's 20 kilograms, and this is 200 kilograms. So we can just order that. Building, car, child. This makes sense because the more massive something is, the harder it is to change its motion. You have to put in more work in order to change that same object to go into a different direction, to stop it, to get it starting moving. So, yes, a building resists the change to motion the most. List momentum from highest to lowest. So we know momentum is going to be P is equal to mv. So then you calculate each momentum. So for the car, that is going to be P is equal to mass times velocity. So this is at rest. So the velocity is going to be for the building. Well, let's do the car first. So the car is going to be 200 kilograms times 20. That's going to be 4,000 kilograms times meters per second. Now for the child is going to be 20 kilograms. And that's going to be moving at 3.0 meters per second. Now for the building, that is going to be 4,000 times 0 because it's initially at 0 and it remains at 0. It's at rest. So 0. So we can rank that number 1 as the car, number 2 as the child, and 3 as the building. And this makes sense that because even though it has a large it has 0 velocity. And when you're calculating momentum, you take into account both. It has zero velocity. Momentum, it requires both mass and velocity. What is the momentum of a 60 kilogram soccer player moving at 7 meters per second north? So we know the mass is 60 kilograms. This is our velocity. So it's simply 420 kilograms meters per second north. A 400 kilogram car speeds up from 3 meters per second to 15 meters per second, experiencing a force of 480 newtons. What is the magnitude of the car's change in momentum? So delta P is equal to m v2 minus v1. Delta P is going to be equal to 400 times 15 minus 3.0. So that's going to be 400 times 12. And that's going to be 4,800 kilograms times meter per second. What is the magnitude of the impulse on the car? So impulse is J is equal to delta P. So that's going to be 4,800 kilograms times meters per second, which we found up here. So these are the same. For how much time did the force act upon the car? So in order to find the time that the force acted, it's J is equal to F delta T. So we know our J is the same as our delta P. Our J we can plug in here. 4,800 is equal to our force. Our force of the car was 480 newtons. And delta T, we're solving for delta T. Delta T is equal to 10 seconds. If you divide 4,800 by 480, you see that everything cancels except for a 10. It's scaled by 10 seconds. A 2 kilogram rock is dropped from rest. What is the rock's speed after it has free fallen a distance of 5 meters? So we can use our kinematics formula of v squared is equal to v initial squared plus 2 times the translational acceleration times the change in y. And since we know that it's dropped from rest, that means that initially it had a velocity of 0. So if we plug in everything, we know that 2 times 9.8 times 5.0, this is going to simplify to v squared is equal to 98. We want simply just v, so we can take the root of both sides, and then you have v is equal to the square root of 98, and that is approximately going to be 9.9 meters per second. What is the impulse imparted on the rock by gravity? So, impulse from gravity, we know that impulse is going to equal to a change in momentum. So first we have to find the final momentum. Our final momentum using P is equal to mv, that is 2.0 times 9.0, that is equal to 19.8, which is approximately 20 kilograms times meters per second. How long did it take for the rock to fall 5 meters? We know that we can measure the change in our height, our displacement, by using the delta x formula and just using delta y instead, because that's just our displacement in the vertical direction. So this is going to be 1/2 gt squared. This is going to be 5.0, which is equal to 1/2 9.8 t squared. This is going to equal to t squared is equal to 5.0 over 4.9. T squared is going to equal to 1.02, and then the root of both of these, t is going to be equal to 1 second. A 2 kilogram mass traveling at 5 meters per second experiences an impulse of 30 newtons second in its direction of motion. What will be the speed of the mass after the impulse is applied? So we can use the impulse momentum theorem, which states that impulse is equal to the change in momentum. So the impulse is equal to m times the initial velocity minus the final velocity minus the initial velocity. Plugging in our values, we have 30 is our impulse, and then we have our mass is 2 kilograms, and our final velocity we don't know because we are finding that, and then we have our initial velocity was 5. So that's going to be equal to 30 is equal to 2vf minus 10. So that's going to be equal to 40 is equal to 2vf, and vf is going to equal to 20 meters per second. A pitcher throws a 0.2 kilogram ball 40 meters per second at a batter. The batter hits the ball back at the pitcher with a speed of 50 meters per second. The bat and the ball were in contact for 0.1 seconds. What is the impulse that was imparted to the ball by the bat? Watch your velocity sign. So what we're given, we can write to the side here. Our mass was 0.2 kilograms. Our initial velocity was positive 40 meters per second, and we're going to define this as toward the batter. And v final, we're going to say is negative 50 meters per second because it is toward pitcher. And our time interval is going to be 0.10 seconds. Now first we have to calculate our impulse. Using the impulse formula, J is equal to m vf minus v initial. So plugging in our values, we have 0.20 minus 50 minus 40. That is going to be equal to negative 18 kilograms times meters per second toward the pitcher, because we've defined our negative direction as towards the pitcher. Now, what was the force of the bat on the ball? What we can do is we know that F is equal to J over delta T by rearranging our previous expression. Now F, plugging in our values, we have negative 18 over 0.1. Now that's going to equal to negative 180 newtons toward the pitcher. See, what was the force of the ball on the bat? Well, Newton's third law states that it will be the same magnitude, but just in opposite directions. So our answer is going to be 180 newtons towards the batter. So it's the same magnitude, but opposite direction. Instead of the pitcher, it's